In order to understand electricity, we first need to review some of the things that you might remember learning in grade 9 about static electricity. And the most important place to start is to remind ourselves that all matter is made up of atoms, and those atoms each have protons, and they have a positive charge, and electrons that have a negative charge. And then we also need to remember that the protons are going to always remain stationary, because remember, they're locked inside of the nucleus of the atom. But the electrons, because they orbit around the outside of the nucleus, they're more free to flow and can actually move from one atom to another. From there, it's also really important to remember what we call the fundamental laws of electric charges. And those are just simply stating that opposite charges, well, we know that they attract one another. In other words, they will feel a force that will naturally pull them towards one another. But if it's the same kind of charge, whether it's two positives near each other or two negatives near each other, they'll repel. They'll naturally feel a force that pushes them apart from one another. And it's also important to note that, for reasons we'll talk about later, some charged objects could actually also attract some neutral objects. Now, from there, we can start talking about how objects even become charged in the first place. Because typically, objects might start having a neutral charge, meaning that they essentially have the same number of protons as they have electrons, and that balances out their charge. But there are various ways that they can become charged. And one of the most common ways is what we call charging by friction. And it gets that name because friction is quite literally involved. Because we take two different objects and we rub them together, which causes friction. And when that happens, we tend to notice that one of the materials might have a weaker hold on its electrons, and the other one has a stronger hold on electrons, and like to pull them over and hold on to them more strongly. And so whichever one has the weaker amount of hold on its electrons, it will give some of them up, and it'll lose some of its electrons. That'll make it positively charged. The other object that has a strong hold on its electrons is going to pull over some of the ones from the weaker one, and it'll get extra electrons. So that'll make it negatively charged overall. And through years of experiments, we've actually determined something called an electrostatic series. And it's essentially a list that's ranked of different materials, and the ranking is based on how strongly they like to gain electrons. We could also think of it as how strongly they hold on to electrons once they have them. So for example, if I took something like glass and I rubbed it with something like plastic, well, the glass has the much weaker hold on its electrons, so it will naturally tend to give up some of its electrons to the plastic. So that will leave the glass as being positive because it's lost some electrons. From the plastic's perspective, it's going to gain some electrons from the glass because it's got a really strong hold on electrons and tends to pull other electrons into it. So it's going to have extra electrons, and the plastic will become negative. So these two objects that might have started as completely neutral, when they're rubbed together, it redistributes the electrons and causes both of them to develop opposite charges. And so after that, we should actually notice that those two objects should attract one another from there. But there's another form of charging that we call charging by contact. And so that doesn't require full friction. We don't really need to rub any objects together. It actually just requires a slight touch. That's why that word contact comes in. And that's when a charged object comes into contact with some second object, which might even be a neutral object, and we end up evenly distributing equal charges to both. So, for example, when a charged up hand grips a neutral doorknob, you might have felt or seen a small spark appear. And what that's doing is allowing some of the extra charges from your hand to escape onto the doorknob. And it will naturally want to do that to try and balance out some of the charges involved. And after that process occurs, both your hand and the doorknob will end up equally charged. But we have to remember that the doorknob was actually originally neutral. So the doorknob started as neutral, but suddenly has its own charge. So that's how we can charge up that doorknob using only contact. And in class, I'll go through a little simulation that'll demonstrate this in a bit more detail as well. A final kind that's a little bit hard sometimes to wrap our heads around is actually not caused at all by contact or friction. It doesn't even require any specific touch whatsoever. And we call this one charging by induction. and we say that charges are induced. And this happens because a charged object might come close to a neutral object, and the charges will push around the electrons inside of the neutral object. And so the neutral object has an even number of protons and electrons, but as soon as a charged object comes near it, its electrons start to get pushed away. They redistribute themselves. And that creates regions within the neutral object that are partially positive and partially negative. Again, that might be a little bit hard to wrap your head around at first, so I'm going to just demonstrate that with a little simulation. So actually what I can show first with this little simulation is charging by friction. So right now I've got a little balloon, and it's a neutrally charged balloon. It's got an equal number of positives and negatives. And I've got a sweater beside it. It's the same. It's neutrally charged, an equal number of positives and negatives. If I rub the balloon on the sweater, the balloon's material, that latex material, has a natural ability to pull electrons and hold them on strongly. So it's going to pull away the electrons from the shirt and become very strongly negatively charged. So now I've got a negatively charged balloon, and I did that just by friction. But what I really want to demonstrate to you is induction. So now if I take my balloon that has a really strong negative charge, I'm going to bring it over to the right here, and I'm bringing it close to this wall. The wall, if I bring the balloon away, I can see the wall just has an equal number of positives and negatives, and they're equally balancing each other out in space. But if I bring the negatively charged balloon close, you can start to see that those electrons get pushed away. They're getting repelled by my negative balloon. So I bring the balloon away, and they're in normal spots, but as I bring the balloon closer and closer and closer, those electrons get pushed away. But you can see that because they're pushed away, the area of the wall that's now closest to the balloon is only positive charges. And so when I actually bring the balloon right up to the wall, now you can't see this from your perspective, but I'm going to unclick or take my hand away from the balloon, and even if we release the balloon, it will now stick to the wall, because that area of the wall right beside the balloon is now positively charged. All of its electrons got pushed farther into the wall. So that positively charged area of the wall will now attract and hold the negatively charged balloon. As I said, I'll revisit this simulation in class and also go through a little simulation that will allow you to see more visually what's happening with charging by contact as well.